Um, okay, folks. Uh, Good evening, good late evening, or good morning, no matter where you're joining from. Thanks to technology, we are able to live stream this across the world and have Howard join us all the way from Portland. Then I'm in India, and so are most of my fellow Bangalore Astronomical Society members. Um, I wanted to quickly start this with an introduction of BAS and what we are and how it all began. I think BAS was interestingly started 20 years ago in 2006 when a bunch of us decided, mostly college students and young professionals who had just graduated and started their jobs, decided that we would meet after meet in person after meeting each other online on an Orkut group. And suddenly BAS was born, and I can't believe it that 20 years later we are still here inspiring people in Bangalore and around Karnataka, which is our state here, to um, engage in astronomy. We conduct star parties, we conduct outreach sessions where we go to schools, especially sometimes in the rural and remote areas of the state, and conduct programs. Sometimes even in the local language, we sometimes go on TV and explain astronomy and science to people at large. We also collaborate with educational institutions as well as um, all sorts of associations and schools to conduct planet watching or outreach events as well as like workshops for where we present a bunch of lectures. You can look at our website, bas.org.in, bas.org.in, to learn more about us. We are entirely volunteer driven. Our website is pretty thin, and most of our activity happens on a Telegram group, which is very active. In terms of upcoming events, we are about to start a star party. This will be the last of the season as April starts to get cloudy. And this star party, I believe, starts on the 19th, but the information is posted on our Telegram group. I think probably registrations are pretty full by now. We usually go into sort of estimation, if you like, for the summer when the weather is cloudy in Bangalore, and then come back sometime in September with workshops in preparation for the clear season, and we start star parties in December. This is our typical schedule. One of the reasons for organizing this talk by Howard, who is a very experienced telescope maker, he's been building telescopes for 50 years. One of the reasons for arranging this talk is to inspire us to work on telescopes or build telescopes during the cloudy months, which is how Portland astronomers solve the problem of cloudy skies. Howard is based in Portland, in Oregon. And with that, let me introduce Howard. I think I first met Howard something like 10 years ago at Jimmy Lowry's place, a common friend of ours who has a 48-inch telescope. And I was mind blown by his sketches. I hadn't read his articles in Sky and Telescope by then. And later I ended up reading a lot of his articles in Sky and Telescope. Howard has been writing for the Sky and Telescope for what, like, I think 15 years now, Howard? Something like that?
Since 2011, yeah, 15 years.
Yeah, okay. And he's been building telescopes since 1969. And he's made a lot of contributions to telescope making. He is also an avid deep sky observer, so he's not just building telescopes, but also using them to observe the night sky. He makes sketches of deep sky objects, and he already spoke to us last year in October on sketching. That video is preserved on our YouTube channel. And I would strongly recommend that you watch that in case you have not, because it's a fantastic talk. And Yeah, I would say Howard has been, in a personal capacity, Howard has been someone I've always looked up to. He really helped me build my telescope, get my 28-inch up and running. And I've bombarded him with emails, and he's been extremely patient. And I've recently learned that I'm not alone in asking Howard for advice. uh, and Howard's telescope design has been widely copied, or shall we say, replicated, and used as inspiration for both commercial and hobby telescopes. And sometimes you go to a star party on the west coast of the United States and look that all, you look at a bunch of telescopes and all their out bearings and all of their drive systems look the same. They're all copies of ours, right? So it's amazing how many people he's inspired into telescope making. And yeah, he has also written articles on telescope making, and his website has a lot of detailed designs of his telescope, and I've heavily relied on those in building my own telescope. So I'm sure, just like Howard inspired me into making telescopes and mods, uh, I'm sure he has the capacity to inspire everyone else here. And I hope this disease for aperture fever by building your own telescopes will rub off on you as well. I'll mention one final thing about Howard. Until last year, 2025, he was the chair of something called the Portland Aldat Workshop, which is now, I believe, going to be renamed as the Oregon Telescope Makers Convention. Uh, and it's a collaboration of professional and amateur telescope makers from around the world. They come down to Portland. Now there's also Zoom, so we do it hybrid as well. And discuss some really cutting edge ideas in telescope making. And as I said, Howard was the chair for, I think, almost 2 decades, right, Howard? Um, Something like
I'm
2 decades.
sorry, I'm sipping my coffee. Did you ask a question?
Yeah, you've been chair of the Altas workshop for almost 2 decades, right?
For I think it was 14 years. No,
14 years.
no, it was 16 years. It was 16
Okay.
years.
Yeah.
Yeah, it was time to pass on the baton to the new people.
Say again?
It was time to step down and let other people take over.
Right. Yeah. Yeah. Last year at the end of the workshop, Howard stepped down, and I had very mixed feelings about that. But yeah, at this conference brings some of the most cutting edge ideas in telescope making. The videos have been recorded and uploaded on YouTube. You can just search Portland Altas Workshop. You'll find really good content. It's mostly on Howard's own YouTube channel, so you can look that up. Where he also has some of his own sketching videos and such. And I'll also point out that Howard's major contribution there that I'm aware of is spray silvering. So he and Rob Brown essentially figured out how to coat telescope mirrors at home by silvering them with a chemical spray system. So you don't need to build these vacuum chambers to illuminize telescope mirrors. So you can completely coat a big, large telescope mirror at home. And he's also made a bunch of other contributions, but I think that to me is the personal highlight. Um, with that, I'll say take it away, Howard. It's the
Okay.
first.
All right. All right. Thank you, Akers. That was a lovely introduction. Um, I am, this is, it's a little bit after 9 a.m. here on Saturday morning for me. I'm not normally awake at this time of day. I keep astronomer's hours, that's for sure. But anyway, now let's see here. Let me, if I can get, oh, here we go. All right. Okay, so anyway, Akers was kind enough to invite me to give the presentation about amateur telescope making, and I'm delighted that he asked me back, because that kind of reinforces my notion that my presentation last October about sketching went well. It's always nice to be invited back. So anyway, I will bring up my presentation without any further ado, and we'll get going. Okay. And let's see. There we go. Get rid of that. All right. So amateur telescope making. This, there we go. Okay. So like Akers mentioned, I've been making my own telescopes since 1969. I was 14. Okay, you can all do the math in your head. I'm 70 now. So I've been at this for a while, and that's stupid. There we go. So I have just to kind of reintroduce myself for those who may not have seen my sketching presentation in October. This is me. I'm standing next to my 28-inch f4 telescope. This is a satellite image, weather satellite image, just to show where I live. And you'll notice how this is covered with clouds. And we are in the midst of our 9-month-long rainy season. We've just had about 100 millimeters of rain over the last couple of days, which not unusual. Sun is shining now, though. I'm looking forward to going out and observing early next week. So that'll be nice. So this, by the way, this where this picture was taken is at a place called Steens Mountain. This in southeastern Oregon, and it is one of the finest places on the planet to go observe that you can drive to because it's at high altitude. It's just a real special spot. That's why I'm so happy. Okay, so this is the abstract, for this talk, and I included here simply because Akers was so enthusiastic about it, and I think I thought it was pretty good too. But just to kind of give you an idea of what this is about, and I'm not going to read it because we're all literate people here. And the big thing here is that you can see I have a star at amateur. Amateur. That means we do this because we like to do it. We do it because we have ideas that we think can make a telescope work better. Or we just like making things. We don't get into all that as we go along. Okay, so let's start at the beginning. Okay, here are Galileo's first telescopes. These are refracting telescopes. They have a lens at the front. These are really quite small. It's amazing he saw what he's able to see with this. So Galileo was really the first amateur telescope maker. Then there's Isaac Newton's 2-inch reflecting telescope. And those are really the two of the three main types of telescopes right there. So in the 17th century was a big time for telescope innovation. Isaac Newton was an amateur telescope maker. Then we proceed along into the late 18th century to William Herschel's 18.7-inch reflector. Herschel started off as an amateur telescope maker, but he graduated to the point where not only did he become one of the finest visual observers of all time, but he became a professional telescope maker. His telescopes were in great demand. He made hundreds of them. Okay, so this is a question that most people think of right away. Why build one when you can just go buy one? What's the big deal? Aren't professional telescopes any good? And of course they are. But I'm not going to answer this question right now. That'll be answered as we go along through the presentation. And at this point, it's good for me to mention that this whole field of telescope making is gigantic. There is so much to this. I'm only going to be able to give you a brief idea on the breadth and the scope, the depth that telescope making has reached to the modern day. But this is a question that the people who have never made a telescope often wonder about. I can tell you how I answered this question when I was 14. I had to build my own telescope because I couldn't afford to buy one. Um, and back then, it was much, much cheaper to make my own telescope than to buy. And so that was my answer. And we all have different answers to it. And you'll probably answer this question yourself as we go along. So there are two main types of telescope makers. The the gentleman sitting here in this photo, um, Jerry Logan. He is and has been renowned. I'm not sure if he's making telescopes anymore, but he just likes making telescopes. He's not much of an observer. He's just he makes a telescope. He uses it for a little bit to make sure it works properly, makes a few adjustments. Then he's on to making the next telescope. So making telescope is his thing, and he does a beautiful job. And then there's people like me. I build a telescope because I want one. I don't want to. Usually, I don't want to buy one from someone, and I think I have an idea that will make the telescope work better for my purposes than one I could buy anyway. So one that exactly suits me. Now, this photo was taken at the Oregon Star Party in 2019. Probably one of the finest Oregon Star Parties, simply because the sky was so magnificent. This is that 28-inch f4 telescope again I'm looking through. And I'm sketching. This is my sketching pad right there. So, okay, so let's go back to my beginning, because this is what I know most about, what I've done. So 1970, I built this 8-inch f4. And the mount I made for it, that was made from just a bunch of lumber left over from the building of our house that my dad said I could use. I saw a picture of this mount. It's called a modified English mount. I saw a picture of it in a book. I thought, wow, that looks really cool. I can build that. I have wood right here. I can do this. So it weighed a ton. It was really hard to use. But it kind of opened my eyes, because I went from a 3-inch refractor to this 8-inch reflector, and boy, were the views amazing. Okay, then, and this is one of the advantages of making your own telescope, you can change it. It's not like a professional telescope where you're afraid to kind of even touch it sometimes. When you make a telescope, you know everything about it. You're not afraid to touch it. You're not afraid to take it apart. You're not afraid to drill a couple of holes in it. And so this is a few years later. I got the same telescope, but now it's on a German equatorial mount. That's me, and that's my sister Marianne. And again, we jump forward to 1991, and now it's that same mirror set, the same diagonal holder, but in a completely different design, where this telescope has a fixed height to the eyepiece, no matter where it's pointed in the sky. So I can just sit in a chair, and it's very convenient to use. This is the form the telescope is still in. And this is a collage of all the telescopes I've had through the years. This is that 3-inch 15 refractor. The cat that just kind of wandered by, wanted to have this photo taken, and just kind of goes on through. This telescope was given to me by my father. This 20-inch f5 obsession telescope I purchased. I made the equatorial platform it's sitting on, though. Again, that 28-inch f4. This is a 12.5-inch f8. This is an 8-inch f3.3. And this is my current big telescope, 30-inch f2.7. And I'll talk a little bit about that as we go along. Okay. And actually, these two are the telescopes I use the most right now, and sometimes the old 8-inch. Okay, so every year at the Oregon Star Party, there's it's called the Telescope Walkabout, and it was organized by Mel Bartels. He has since passed on those duties to other people, and essentially, it's just people who have made a telescope. They will talk about the things that they liked about what they built, things that they wish they would do better, would have done better. And it's really educational. You'll go around, it might be like a dozen people talking about the telescopes that they have. And it's really educational. So I'm going to try something I haven't done before. Hopefully this comes through. Okay, okay, I think we're still screen sharing. So these are some of the telescopes on a telescope walkabout. And people are talking about, this is really unusual.
I don't think that came through, Howard. At
You're
least
not seeing it?
I'm not seeing it.
No? Okay, well, doggone it. Okay, it says I'm still screen sharing, so you must still be seeing my
Yeah, I think you may have to
presentation.
put the presentation mode and then get back into it. That might work.
Yeah, okay. All right, so never mind on that part. Um, and so just take my word for it. There's just all variety of different type of homemade telescopes. And it's really inspirational because most of the things that people make are really straightforward. And half the time I go, wow, why didn't I think of that? What a great idea. It's a terrific way to be able to share what people are doing. Now this, this is a 2D CAD drawing that I made before building my 28-inch f4 telescope in 2004. Um, and off to the side, you can see that the copy there is that you don't need to have a fully equipped workshop to be able to make a telescope. You can design your telescope. You can design parts of a telescope and have someone else make them. And we'll be getting into that here real soon on how that can be done. So anyway, this is the first time I had used a computer drawing program. And the greatest benefit was that when I had all my parts and I was putting the telescope together, everything fit. Amazing, huh? So to me it was because previously I was either not making a drawing at all or just doing a quick pencil sketch, and sometimes things didn't fit. Okay, so there's that 28-inch when it was brand new. This is in 2000, actually 2005, I think. And yeah, it was a great telescope. Okay, now it's been transformed into this, a 30-inch f2.7 telescope. Yeah, it went from this to this. There's a bit of a story on why, and it's germane to the whole point here of telescope making. Why would I go from a 28-inch f4 to a 30-inch f2.7? Well, in a word, it's weight. The mirror, which you can see here, which is not coated yet in this photo, weighs about 40% as much as the 28-inch mirror did. So it's much, much lighter. And because I silver my own mirrors, it's a lot easier to pick up out of the telescope, spray the silver coating on, and then put it back in. And that's really the only reason I made the change, just because it made it easier to silver. But okay, I needed to redesign this whole top end now. Okay, now the weight distribution of the telescope is completely different. So I made a 3D file of the whole telescope, not just the top end. And this probably won't show up because the other one didn't. So I won't click on that link. The cool thing about making a 3D file is not only do you get to spin the object around and see it from any perspective, is that now you can send that 3D file off to some place that has a CNC machine if you need a part cut out of metal or wood or plastic, and you'll get exactly the part back that you wanted. You can also send a file to a shop that has a water jet cutting machine, and they can cut out pretty much anything. In fact, these altitude trunnions on my 28 and now 30-inch telescopes were cut on a water jet machine. And this is back in 2004. So this has been around. I mean, it was old technology then. Yeah, you think water jet, it's really quite amazing. It's high pressure stream of water mixed in with grit. And it cut through 3/8 inch thick aluminum like it was butter. So this can cut through, thick metal without any problem. There are comparable laser cutters, but they're best suited for thinner materials. So, and then with the 3D file, you can also 3D print parts now. Many people, I know, most of the people who make their own telescopes have 3D printers. I do not, at least not yet. I can imagine that being in my future, but I don't have one yet. The option to having your own 3D printer is to send your 3D file off to a company that will print the parts for you, and then they ship them to your address. Both things work really well. 3D printers, a few $100s, US dollars. So not cheap, but not incredibly expensive. Okay, so let's see if this works. Okay, there's always an ad. Yeah, these are short. Okay, this one's even shorter.
Obsessed with the game.
Yeah.
Get ready for launch.
All right, here we go.
This is a 3D printer. It takes three-dimensional models saved on your computer and physically creates them right before your eyes. 3D printers are both fascinating and complex. Each year, the technology gets better and better. In this video, I'd like to walk you through one of these machines to show how it works. My name's Jared. I create 3D animations to show and explain how things work. Hit the subscribe button to be notified about future videos just like this one. This video is sponsored by Bamboo Lab. In science fiction, they sometimes have this device called a replicator. You can ask it to make almost any object, and it somehow materializes right in front of you. Today, we don't have replicators, but the 3D printer is starting to do some of the same things. It doesn't happen instantaneously, but it's still quite impressive at what it can do. 3D printing is a type of additive manufacturing. You start with nothing and then add materials layer by layer until it's complete. Compare that to subtractive manufacturing. Start with a block of material such as metal, and you remove parts from it to form the final product. Notice all the excess waste. With additive manufacturing, there is much less waste of materials. This is an advantage to 3D printing.
Grip,
Yeah.
stability,
Sorry,
precision.
these were unavoidable. Fortunately, they're short. There we go.
Yes, it's true. A 3D printer can be used to create all sorts of toys, minifigures, movie props, you name it. But keep in mind that a 3D printer can be used to create objects that have a more practical use. A lid holder for your kitchen, zip ties, adjustable supports for just about anything, a Wi-Fi QR code sign, and even a customized broom holder. Very useful for your kitchen. You can even 3D print accessories for your 3D printer. You're only limited here by your imagination. In the real world, there are some other interesting uses. 3D printed food, yes, it really is edible. 3D printed clothes, and 3D printed prosthetics for those that need replacement body parts. Large-scale companies are using 3D printing to manufacture products because it's less expensive and quicker to produce. Companies like SpaceX are literally 3D printing parts of their rockets. NASA is hoping to use 3D printing to create items when astronauts are far from home. This means they don't have to bring as many tools and spare parts into space. And there are even 3D printed houses. Instead of plastic, they are made with a special concrete-like material. And yes, people actually live in them. It looks quite nice if you ask me. There are different types of 3D.
Okay, so I think that gives the idea of what 3D printing can do. It's really an amazing technology for making the smallest parts to the houses. It's pretty amazing. Now this slide is for the 114 millimeter Hadley telescope. All these parts here, where my cursor are going, are 3D printed. Now these are aluminum struts, and this rocker box is made out of wood, but you can 3D print these parts and make this entire telescope for around $100 US. You can buy the pieces already printed. You can get the files, print them yourself. You can send the files off to a company that will print them for you. Again, it's the type of thing where you're getting the parts made here with 3D printing, additive manufacturing, and the big thing though is that if you don't like it the way it turns out, you can modify it to a way you think is going to work better. In fact, there's a company here in Oregon called Analog Sky, and what they sell are the biggest binoculars you can buy, as you can see. This is an 8-inch binocular telescope, and it's almost entirely 3D printed. And these are, I think, 50 millimeter binoculars, also all 3D printed. And they have these wonderful videos showing how to assemble and how to print everything you need to know about doing it. And again, here you can either purchase their 3D files, you can buy the completed 3D printed parts from them. They'll even sell you a completely assembled binoculars as well. So this is the way telescope making is going. Okay, now this isn't amateur telescope making now, although the person who started this did start out as an amateur. Now he's a professional. It's like John Herschel. And if you want to find out more, just search for 3D printed telescopes, and you'll find this is just the tip of the iceberg. There's many, many more. And I think the next slide, yes, this slide, we'll watch a little bit of this, and then we'll see the same commercial. My apologies. But,
Which is closest to the average American's credit card debt? $1,000, $5,000, or $10,000?
We'll never know. Okay.
When it comes to a lot of
3D
things
printed
in life,
telescope.
bigger isn't always better, but that doesn't really apply to telescopes. The 6-inch telescope I built last year has been great, but of course it left me wanting more. So I doubled it and built a 12-inch. It's actually 12.5 inches because that's the size mirror I found for sale used on the Cloudy Nights forums. This is for visual use only. My astrophotography days are behind me. I just want to enjoy the simplicity and beauty of observing the night sky with my own eyeballs.
Okay, well, we'll stop this one here. And go on to this next one. Now, this is the same guy, same telescope, but now he's talking about some of the things that he improved and just how easily it's done with 3D printing.
My 12.5-inch Dobsonian telescope that I designed and built has been great, as I'm sure you've heard many times on this channel. However, there are some aspects of the mechanical design that I haven't been quite satisfied with, so I made them better.
Well, stop.
The large altitude gears simply rest on the smaller roller gears, which in practice works, but it's not ideal as the gears are loaded radially. And gears are not intended to take load this way. They're really only intended to take load tangentially as the gear teeth push against each other. My new design incorporates a smooth surface on the outside edge of the gear. This supports all the radial load, basically all the mass of the telescope. So the gear teeth are just doing the pushing or the rotating as they're intended to do. I've also increased the modulus of the gear teeth from 1 to 1.25, so the gear teeth are a little bit larger, have a little bit more bite. Another improvement is how the large gears are broken up into smaller printable size sections and then rejoined. Someone commented on one of my videos suggesting to split the gears along the tooth profile rather than just cutting straight through. This is so that when rejoined, there'll be minimal or zero seam. This was quite a bit trickier to model. However, I'm always up for a CAD challenge. Not a CAD challenge, a CAD challenge. No, I'm up for a CAD challenge too. Like challenging. The next area to improve was the gear roller supports. In the original design, I was kind of trying to do too much with one part. The vertical bearing supports also function as part of the clamp for the carbon tubes for the main telescope.
So, okay, so that gives the idea, excuse me, of how easy it is to modify a 3D file based on real world experience with the first iteration. Like the guy said, the first version worked pretty good, but he thought he could make it better. And with 3D printing, it's really straightforward to try the idea to make it better.
Base.
Okay, so now I know that traditionally amateur telescope making has been associated with mirror making. Like I've made about a dozen mirrors through the years, and it's an incredible process. It's not complicated. It's not really even all that sophisticated. But it requires a tremendous amount of motivation and determination and willingness to really, really think about what you're doing at times, especially in the final stages of trying to get the exact parabola that you're trying to get. So this is just a couple pictures here to show kind of the traditional. This is the polishing lap and the figuring lap. Yeah, it can be a little messy, but it's so straight. I did it when I was 14. I'm not a genius. I'm not an idiot, but I'm not a genius. And so it's not the type of thing that requires any specialized skill. I was just determined. I was going to make this thing, and finally I did. Okay, and then the final part of making a mirror is testing the optical surface. Mel Bartels, who will come up here again in just a little bit, he has come up with a testing method using the Ronchi bands, and that's the shadow bands here on the surface of the mirror can be inputted into this program, and it'll tell you exactly how good or how bad that surface is, and will show you where to concentrate your figuring work going forward. It's really a magnificent feat of programming to be able to figure this out, because until this point, these Ronchi bands wouldn't tell you anything other than, oh, well, look, the mirror looks smooth. Okay, so and here's Mel. He's holding his newly spray silvered 30-inch mirror. You can see how thin it is. 16 millimeters thick all the way through. So this is like a big contact lens. It's not thicker, it's not thinner in the middle and thicker on the edge. It's the same 16 millimeter thickness all the way through. It's a meniscus-mirror, which means that it's very, very light compared to a full thickness, i.e. a 2-inch, 50 millimeter thick mirror. In fact, this piece of glass started life off as a glass tabletop that through incredible amounts of work and engineering was transformed into this beautiful 30-inch mirror. Now, okay, so 30-inch f2.7, that's what's in my telescope, but not this mirror. Mel made two at the same time. And then when he was finished and it dawned on me just how much lighter these were, this is only 40% the weight of my 28-inch mirror. It's a big difference. It's a huge difference. This mirror is easy to pick up. The 28-inch mirror is at the limit of my strength now, and so I'm glad that it's off making someone else happy now. So for if you're starting to feel like maybe I could make a telescope, 3D printing or 3D files and having parts made. I'd say for your first attempt at a full telescope, just buy your mirror. Getting into the process of making the mirror. Making the mirror is more difficult than making the telescope, the rest of the telescope. And it can be really discouraging at times. So, if you already have a telescope, you can even make a new telescope mount for what you have, for the mirror you already have, and put that in there. So you don't even need to get a new one. If you have ideas that there's something about your current telescope that you really don't like, you can design something that you think will work better, and off you go. Suddenly you're a telescope maker. Now, a little bit about spray silvering that Akers mentioned. This has really been a wonderful, wonderful thing, in my opinion. Up until, let's say from about the 1860s, when the first glass mirror substrates were used, because up until then, reflecting telescopes, their mirrors were made out of metal. It's called speculum, and it wasn't very reflective. At best, is like 65, 66% reflective, which is pretty shiny, but compared to 90 and 95 and 99% reflective, it kind of sucked. And then in the 1860s, Leon Foucault of Foucault pendulum fame, he's kind of a polymath. He came up with the system of being able to chemically deposit silver on glass. And he was the first to really demonstrate the process successfully. And then through the 1930s, that was the way all telescopes were made: a glass substrate with a silver coating. And it's right at that point that two things happened. Aluminum coatings came into being in a vacuum chamber, and at the same time, spraying the silver chemicals onto the glass came along. Aluminization really won out, especially for the professionals, because aluminum coating is more durable. It doesn't tarnish. And the way they were making silver coatings back in the day was that one of the final processes was that they would buff the surface of the mirror to get rid of any impurities left over from the chemical deposition process. And that introduced a lot of tiny, tiny sleeks, tiny little scratches into the silver, which in the telescope produced stray light. That's not a problem anymore with spray silvering. I won't get into the details of spray silvering other than to say that, one, even I can do it. I'm not a chemist. It's really straightforward. 90% of getting a successful silver spray coating is making sure that the glass is perfectly clean. And I use the word perfectly on purpose because it has to really be perfectly clean. It can't have any contaminants or the silver won't adhere. And what I'm doing here, this is my hand. This is a cotton swab. And this white stuff is calcium carbonate, lab grade. So there's no impurities. And that's all you need to use to clean the glass. But you have to go around and around and around and around. It takes a long time to get it perfectly clean. Then you have to rinse it all off with distilled water. Again, I'm starting to get into it. So suffice to say, a new silver coating and a telescope mirror will give you from the low 90s for the blue wavelengths to mid 90% for green wavelengths and the high 90s for the red wavelengths. And it's just it's magnificent. Okay, so back to this question. Okay, why build? Well, I've kind of been answering that bit by bit as we've been going along. But again, this is a personal decision. I mean, there's no one answer that suits everyone here. Just like there's no one telescope that suits everyone. If all of your observing desires are being met by the telescope you bought, you don't need to make one. But that's kind of rare when everything just works the way you want it to. Maybe it's just the one little thing that you want to fix. So making your own telescope is really not that less expensive. In like 6, 8, 10-inch size telescopes, the bigger you get, the more money you start to save. Like I saved many thousands of dollars making my 28 and 30-inch telescopes. I mean, there's no denying that. But how many people want a telescope that big? It takes a lot longer to build a telescope than to buy one. You may feel unprepared. I mean, really, who's prepared to make something like this unless you're a machinist? Really? And yeah, I totally get that. When I started making my first 8-inch in 1969, I had no idea what to expect. I hadn't even designed the whole telescope. I just knew that I needed to start with making the mirror because without that, nothing was going to happen. Oh, and it can be frustrating. When I was first making my 28-inch in 2004, my little workshop was in our basement, and my wife Judy was very supportive, amazingly so. And for the first month, I would come back out of my little workshop on the weekend, and she'd ask, "Well, how's it going? And, things going well, blah blah blah." She's very interested. And then as the months went by, it took me 6 months until the telescope was assembled. But somewhere in there, she went from "How's it going?" to "Is that damn telescope finished yet?" It frustrated her because it took so much of my time. And so I was more married to my making my telescope than to her, it seemed like. And she had a point. I needed to kind of cool it by giving that project my entire time. So a lesson learned there. It's easy to get pulled in because you want to get it done, but it's frustrating sometimes. You're trying to figure out how to do something and it just doesn't come to you, but eventually you figure it out. or you have no idea how to begin. I mean, how do you learn? How do you learn how to make 3D files? Um, how do you even design? How do you think about designing? I mean, these are all things that if you have no experience at it, you have to start from the beginning. Hey, we got the internet now. Anything you want to know, you can find out on the internet. When I started out, I had one book. I still have it. It's kind of more of a pamphlet, actually, that came with the kit I had purchased for 35 US dollars for making the mirror. And that told me everything I needed to know at that time for making that telescope. But now we have the internet. If you don't have an idea how to begin, you can find out online. Or maybe you don't have a space to put a telescope together. Well, I get that. I don't have if I wanted to make a telescope mirror now, I couldn't do it. I don't have space anywhere in my house or in my tiny little workshop in the garage. There's no space. I would have to get rid of something that I know I already need. So that's just not going to happen for me. but okay, what are the positive things here? Okay, the big one is personal satisfaction. After you've made something and it works, there's a feeling that I Akers told me that many of you are software engineers. It's probably very much the same feeling you get when your program works. You put a lot of effort into it, you debugged it, everything is doing what you wanted it to do. Same thing with the telescope. When you make a telescope, or even just a little part of a telescope, it worked. That's a great feeling. You can learn new and interesting skills. It took me a little while to learn how to make 3D files. I started with SketchUp, which is you can get a free version online, and you can purchase a more fully detailed version, of course. But there are many other 3D programs that you can purchase and use for really a minimal cost. Yeah, it's a learning curve, just like any other program, but you can learn it, and it's very interesting. Okay, and you end up with something that suits you. Not everything suits everyone. There are very few things that suit everyone. So if there's something that bugs you about your current telescope, yeah, you can do something about that. Start small. That's always a good place to start. Pick one part of your telescope that bugs you and see if you can figure out how to make it work better. Okay, now I could have summed up the whole reason why to make a telescope in this slide here. This young woman on the right, she made that 17.5-inch telescope by herself. I came across this on the Cloudy Nights forum. You can see the URL there at the bottom. She goes by the name Brisby2 on Cloudy Nights, and that's her comments at the top in italics. But forget the telescope, the particulars about the telescope. All you need to do is look at her expression on her face. Okay, that's the feeling of accomplishment and personal pride. I get it. I totally get it. And if you've ever made anything at all, whether it's a physical object or a computer program, you know what that feeling is like as well. Okay, so here's an example of something simple. Okay, most commercially made Dobsonians have this little tray where you put your eyepieces. Okay, that's real handy, but it's also a great way to make sure your eyepieces get covered with dew during the night. So this friend of mine, Lauren, she designed this little lid. She found this, I don't know where she found this little tray, but she rigged up this little hinge so she can flop this down over the top of her eyepieces when she doesn't need to grab one. Perfect. Keeps the dew off. Oh, and look, she's got this little bag she attached where she can put some doodads in there and not lose them. Stuff like that. This is amateur telescope making right here. This is solving a problem that the telescope she purchased didn't take care of. Here's another big thing that commercial Dobsonians really don't get right for the most part. And that's using real Teflon. There are 3 Teflon pads. This is the ground board of a Dobsonian. You've got the 3 Teflon pads, and then you have this bumpy laminates surface. There's many different kinds that work here. And then this 4th Teflon pad in the middle. This makes the Dobsonian move like butter. And that feeling so completely enhances your observing experience that if you can't use your telescope without frustration at high power, then you need to look into getting some Teflon and laminate on your azimuth bearing of your telescope. And the same thing for the altitude bearings. Again, these are strips of Teflon. These are 2 strips of laminate, a different kind from over here. But the thing about Teflon and these laminates is that they have about the same coefficient of friction. So there is no stiction when you start to move the telescope. It just moves smoothly, without bumping along or crunching. It's just utterly smooth. And when your Dobsonian moves like that, then you can use high power without any problem. So your telescope really is an extension of your curiosity, and making sure that it doesn't get in the way of your observing for your personal journey of exploration is important. If you're fighting your telescope at any point when you're observing, it can be improved. And these are ways that you can think about approaching and actually doing something about making your telescope work the way it should. And I'll end on this slide. This is this beautiful image. This is a place here in Oregon called Crater Lake. It's the caldera of a volcano that exploded and collapsed in on itself several thousand years ago. And then this quote is one of my favorites. Jennifer Willis writes on the Sky and Telescope website occasionally, and this quote is really hits me in the heart because, yeah, the night sky brought me back to myself. I mean, and I think for anyone who's observed the night sky can feel that some of that same sentiment. So, and having a telescope that doesn't get in your way of enjoying the night sky and letting all your earthly cares go. Yeah, that's important. That's an important part of it. And if you don't do anything at all with making even a tiniest little part or improvement to your current telescope, or making it a completely new one, if this doesn't interest you at all, at least I hope you have an idea of what's possible out there and how telescope making has progressed through time to the point now where 3D files and 3D printing and CNC machines and water jet cutters make so many more things possible than they had in the past. And so that is my presentation. And let's see, how did I do on time? Well, not too bad. Okay, so I guess I'll stop my share. And there we go. Okay.
So Howard, am I actually audible?
Yes, I can hear
Okay,
you.
great. Because I changed over to a headset after the complaints about my voice echoing. I wanted to know how much time do you have for questions?
Oh, I have all day.
Okay.
So, it's only 10 o'clock in the morning.
Okay, so I encourage people on Zoom to use the raise hand feature or simply unmute themselves and ask questions. And try and alternate. There's few questions on YouTube. I will be relaying the questions from YouTube onto Zoom. So please feel free to ask questions on YouTube, and I will relay them. And yeah, people on Zoom can unmute yourself and ask, and we'll try to alternate.
All right, I'll go. I'll
Okay.
go. Thanks for the talk, Howard. It's very interesting presentation. Here's my question. For quite some time, I was thinking of building a telescope, and then later on, I decided not to build one and ended up just buying a 12-inch scope. Now, and these days, all that I'm trying to do is doing minor tweaks. I mean, if I don't like the position where my current tel rad is, I'd like to switch it, or I want to do something, add a eyepiece holder or something like that. Minor tweaks. But building an entire telescope is a whole different ball game. Now, in your experience, what's the biggest obstacle? What's the toughest part when it comes to building a scope ground up? Is it mirror making? Is it doing the work, working with all the wood? Is it the working with all the metal? What's the biggest challenge?
The biggest, well, there's two big challenges. The first one is motivation. So what I have found is that when I'm properly motivated or sufficiently motivated, I just find a way. I talk to people, I make inquiries, I look online, I just find out how to get going. But in the actual of making things, I've been fortunate because I've always had a place. Well, not always. There's a time when my workshop was also inside my one-room apartment.
Oh,
But it just came down to it. God, I've got to make this. I've got to do this, and how can I do it? Okay, well, I have to bring it in my apartment. All right. Well, this have to be neat. I'll put down a tarp on the floor and this and that, and so it worked. I didn't try to do everything all at once. Um, I let things happen in a natural cadence. I had work, I had family, I got this and that, and so um, you know, collecting enough tools to make a telescope yourself is, if you're starting from that standpoint, that's the most expensive part, is buying the tools. In some cases, depending on the size of the telescope. Um, that's why I'm really enthusiastic about 3D files, because you make a 3D file of what you want, you send it off to a shop with a CNC machine, and they'll cut those parts out of any material you want. So you don't need a whole lot of tools. Basically, at that point, you might need a few screwdrivers, um, a little handheld drill, and some sandpaper, and that might be all you'll need to be able to assemble a completely new telescope. But again, it comes down to how motivated are you to really do it. Because I will say that there have been times when I'm in the midst of making something where I just want to just walk away, and I want to do something else. It just isn't working for some reason. These parts aren't going together the way they're supposed to, and then I step away for a day, and it all comes to me. No, I needed to do it a different way, and then I do it the different way, and that works. And progress is made in steps. Akash knows how this goes. Look at the smile on his face. It can be a challenge. and it can go really easily. It's an individual thing. Some people have a real knack for this, and others, it's just like learning ancient Greek. It's hard.
Mhm.
The reason for the smile on my face is I remember two excellent pieces of advice I've heard from you. One is a telescope is never finished. So always, it's okay to make mistakes and correct them and iteratively develop. You don't have to get it right the first time. The second is procrastination is actually a powerful tool to let the subconscious mind do its work. And you actually think about designs passively when you're in the shower or when you're driving somewhere or whatever. And eventually you'll actually do it better when you get back to your desk and try to work. So I feel less guilty about procrastinating on my telescope
Yeah,
now.
no, that's exactly right. That's the procrastination. Yeah, kind of the word kind of has a negative connotation, but it really does, like you said, it just gives your subconscious time to work on the problem. And I'm real good at waking up in the morning going, of course, I should have done it this way. And I will say a lot of those I should have done it this other way don't work. So it's a cumulative process of finding the solution that actually does work sometimes. But telescopes don't have to be complicated. Basic Dobsonian, it's not that sophisticated. It doesn't have a lot of precision parts. In fact, it doesn't have any precision parts. Um, so that's why it's kind of the amateur telescope makers' um, point of entry. I think it's the simplest, most straightforward design to make, but it comes in infinite varieties. Go online, search for Dobsonian telescopes, and you'll see so many different kinds.
I have one quick follow-up question here. How come I noticed that all your telescopes they're all pretty fast. It's a f3.3, f2.2.7, f4. Why is it? What do you have against planetary viewing?
Well, nothing. I really enjoy observing the planets. The and one of my telescopes was a 12.5-inch f8, and that worked wonderfully well on the planets. Um, but I've also found my f4 telescopes work great on the planets too. Um, some of my best planetary views have been through my first mirror, the 8-inch f4. And the reason I started at f4 is because I didn't know that was supposed to be too hard to do for a beginner. It's also why it took me longer to do than it might have if it was an f7 or f8. But a well-made f4 mirror or f3 mirror can give excellent planetary images. Maybe not quite as good as an f8 can, but it's very satisfying.
Okay, thanks. Thank you very much, Howard.
You're welcome.
Okay, I'll relay a question from our YouTube chat. And there's a few more questions on Zoom we'll come back to. So the question is, has anyone in amateur land managed to make a segmented mirror telescope, like combine multiple small mirrors to effectively create a large primary? I guess this requires you to face the mirrors. Or almost do something like adaptive optics, which is have actuators. Has anyone in amateur land tried segmented mirrors made from multiple segments?
I have seen one attempt at a segmented mirror, and it didn't have any active controls. It was basically, it was very interesting, actually. It was a 60-inch diameter disc of, I forget what the base material was, but the person got a bunch of small mirrors, maybe about 3 or 4 inches in diameter, and he epoxied them onto this surface. And then he ground and polished that, just like he would if it was a single mirror. He never got it to where it produced an acceptable telescopic image. At best, it would form a, if you pointed out the sun, it would form a fairly small disk, but it just wasn't precise enough because the adhesive he used didn't hold each of those segments in the same way, I think. And also, it was a really, I think it was probably too big way to start. I think doing something like that could be possible in smaller aperture to work out the details. But as far as computer controls, to actively control several mirrors to form a single image, I haven't heard of anyone being successful with that. It would be quite the apparatus to be able to control that, because you would need to have actuators that can move on, basically in the submicron level to be able to actively control a whole bunch of mirrors. Now, of course, if professional observatories have figured this out, but they have very big budgets to be able to do that, and most amateurs do not.
As a follow-up to that, do you know of any literature on this that amateurs can access? Like, where would you, if you were to take up this project? I know many of us in the Altas collaboration are really adventurous to take up such projects. So, like, where would you start if you wanted to take up something like this?
Well, there's probably, I'd start online. I have a book. I forget the name of it. Let's see if I can see it. Oh yeah, the design and construction of large optical telescopes. There's a chapter in that book, I think, about this sort of thing. This is an interesting book because it's written about how professional telescopes are made. The design and construction of large optical telescopes. Yeah, it's right there behind my monitor on my bookshelf. So yeah, it would be a really interesting challenge to be able to figure that out, because you also need to have an active control loop, so such that the computer controlling these actuators is getting feedback from the image showing how sharp it is. So that type of feedback loop could be quite the challenge, and it could be very interesting programming challenge, as well as the mechanical challenge.
Okay. Hi there. I have a question. So, I'm trying to build a, let's say, 6-inch telescope, but unlikely that I found any material online because the F ratio is a bit different, the mirror I have. So, when it comes to the math of it, like how do you deal with that? Let's say I'm building something like a travel tub where it's similar to your 28-inch. Let's say I don't know how to like architect the bearing, altitude bearing. So, would you go for like something online, or how would you know that exact measurements and everything? Like when you are building from scratch and you don't find it online.
Well, there are
Is
two
it
two
is
ways
it
to do
only
it.
that you actually build something and then experiment and then is it trial and error, or is there a better way? Is what my question.
Yeah, yeah. Well, that's one of the ways. You can just give it a shot and see how it works, or you can calculate it out in advance. I've tried both ways, and they both work. I'm not a really good. No, I'm not much for calculating things in advance. I mean, I can do it, but I would just assume. Well, so let me just back up a little bit. First thing is I just look at what have other people done that I know works. And I'll look at it and I'll try to think, okay, why does that work so well? And then, when I have an idea why it might work so well, I'll use that as a starting point, and I'll copy that as as needed, and I'll make adjustments if needed. And so that'll be my first attempt. And that almost always works for me. I don't know, maybe I just have a knack for it. I have very good friends who will calculate everything out in advance, and they hit it on the nose. They're on their first attempt. So you can go both of those ways. But it's hard to go wrong by following what has already been done.
Got it. Yeah. Thank you.
Okay, I'll take the next question from YouTube. Any lightweight material alternatives for a glass mirror?
Well, I have read about carbon fiber composites as a substrate for telescope mirrors, and I know that was being actively explored by NASA for space telescopes. Metal substrates are used for space telescopes. Beryllium, I think, is what was used for the James Webb telescope mirror segments. Yeah, it's a and a friend even tried making mirror substrates out of glass foam, which is pretty much just what it sounds like. It's just glass that's been foamed. And he had a kiln, and he would adhere a thin plate of glass to the top of that foam. So it was just a version of a glass substrate, but it was very, very lightweight. The thing about a substrate is that you want it to be as stable as possible in all temperatures, and be able to have a surface that can be worked to put on a very accurate optical surface. And some have tried making they make a regular glass mirror, and they use that as their template, and then they'll put another material over the top of that to try to capture that precise optical surface, and then use that to make other mirrors. And that doesn't really work that well, unfortunately. It's a cool idea. So there has been research into it, but for Earth-based telescopes, glass substrate seems to be the best all-around choice. Pyrex or borosilicate glass is preferred, although plate glass works really well too. Plate glass is a lot less expensive, and it tends to cool off faster than the borosilicates, and have a slightly better or a slightly smoother polish to them. Now, that's what I know. There's probably a whole lot more about that online, but yeah. So I'm not claiming to be the world's expert in all this stuff. I'm just telling you what I know.
Howard, good morning. It was really nice hearing you and a wealth of information. My question is, wouldn't building a telescope be more easier if it is done by a group of maybe 2 or 3 like-minded persons rather than do by oneself? Are there any pros and cons on group functioning?
Yeah, well, it could be, but I think the key there is what you said, like-minded. If you have a group of people and you all have different ideas on how to do stuff, then things really go slowly. I know several projects that have taken decades because the group couldn't agree on what was the next thing to do or how to do it. Yeah, but if you have friends and you want to do it together, and you're all on the same wavelength, oh gosh, yeah, you betcha, because you'll each have different strengths probably. and the combination could end up making a wonderful instrument.
Yeah,
Plus
thanks, Howard.
plus I would say the social aspect would make it way more enjoyable than doing it by yourself. Doing it with friends, doing anything with friends is better usually than by yourself.
Okay, thanks, Howard. Thanks for your inputs on that.
Okay, I guess the next question from YouTube. Yeah, this is an interesting one. Can you summarize the devices you use to see the M1 pulsar visually, and if they can be made by amateurs? I think Chetty is essentially asking about the chopper made by Dan Gray. So take it away, Howard.
Well, yeah, I've seen the pulsar in the Crab Nebula blink was one of the, next to a total solar eclipse, is the most incredible thing I've seen in a telescope. Making a rotating shutter, which is all this is just a disc with a small cutout that is rotating just slightly different than the period of the pulsar. I don't remember if Dan made his to rotate slightly faster or slightly slower, but the result was that the pulsar, and this is looking at the pulsar through a 90-inch telescope in Kitt Peak in Arizona. Smaller telescopes, this doesn't work visually. I'm sure it would work photographically. But anyway, in the 90-inch telescope with that shutter, the pulsar would brighten and dim and brighten and dim and brighten and dim. It was incredible. Yeah, and I have read accounts that there have been a few people who have been able to detect that actual 30 beats per second change in the pulsar with just their eye. They just were able to see that fast flickering. It's not that much different than a motion picture film in a theater, which I think is 24 frames per second. And some people can see that as well. So it's not everyone can, but I've just read of people who can.
I actually heard a talk by Jocelyn Bell Burnell, who discovered the pulsar, and he said that there were certain young women, especially, somehow they have a tendency to be able to see the Crab pulsar blink. And so apparently somebody actually discovered it visually, but people dismissed it, saying you're looking at stars twinkling.
Yeah,
right?
exactly. Yeah, it's been my experience that women's eyesight at times can be much more sensitive than us poor males.
I don't see any questions on Zoom at the moment, so I'll take, there's like 3 more on YouTube, so I'll pick the next one from YouTube. Yeah, so when you silver mirrors, how long have you observed practically the silver to last?
So how long in between coatings is that? How long does a silver coating last until I have to redo it?
Yeah, I think that's essentially the question.
Okay, so it depends, like most things in life. Where I live, it's a very moist, damp climate, and silver tends to tarnish quickly in the presence of moisture. But the silvering process now has the substance called, professionally is called Midas, but it comes from the superconductor industry, that it's a liquid that you put over the brand new silver coating, and you let it soak in for like 5 minutes, and then you rinse it off, and that protects the silver from tarnishing as quickly as it would otherwise. It doesn't prevent tarnishing, but it slows it down maybe 10 times. So I think I resilver my mirrors every 2 years, year and a half, 2 years, depending on how much I observe on humid nights, which is unfortunately a lot. So yeah, but the other side of the coin is that I don't have to clean the silver coated mirror, because when it gets dirty, I just put on a new coating. It only takes a couple hours, which is pretty much the same amount of time it took me to clean an aluminum coating.
Okay, there's one more question. Any practical considerations or advice on building an artificial star for star testing a mirror?
Building an artificial star, I've never done that. I've read about it. And things I've read range anywhere from making a material, finding a thin, opaque material that you can poke with a needle very, very carefully to get the size hole that you need, to having a device made at a machine shop that does the same thing. Or you can actually buy these online too. So it's you have options as far as that goes. An artificial star can be really useful, but you also need to be able to place it far enough away, which is oftentimes hundreds of meters, to be able to give you the information you really need. So if you have that kind of space where you can do that, that's a really good option. Especially in climates where it's really cloudy and rainy and terrible weather.
Okay, I think we've answered most of the questions on YouTube and Zoom, but I have one. How did you learn CAD and the entire
Very,
CNC
very
workflow?
slowly. Yeah, the 2D CAD program was I think it was called TurboCAD. This was in 2004, and yeah, actually it turned out to be fairly easy by trial and error. It was fairly intuitive. Um, the 3D program I started with SketchUp. I knew other people who were using the Mel Bartels in particular, and so I just looked that up online, and I started to use it, and it was not as intuitive, and so I was online a lot asking questions in SketchUp. How do I make a hole? How do I make a part that is thicker? How do I make I was constantly asking these questions until I could do the basic things. And fortunately, there are a lot of videos online about how to do things in SketchUp. So there's lots of little short tutorial videos, and yeah, but that may not be the best 3D program. There's lots of others. Basically, you need a program that can make a DXF file, because that's what 3D printers and machine shops like.
Follow up to this is, how did you make telescope parts before CAD? I know you've shown me your router and the circle cutter and things like that. But if you look at Dave Craige's book, for example, there's no CAD in it. So what do you think has changed because of CAD and CNC, which I think personally, to me as a telescope, a new novice telescope maker, if I can CNC something, it makes my life a lot easier because I don't have the skill to do the hand tooling. So how do you contrast these two eras of telescope making, before CNC and CAD became accessible to amateurs versus after?
Yeah, well, before 3D files and printing and CNC machines and all that, yeah, you needed saws, you needed routers, you needed a bunch of tools. Or you just needed one little handheld saw and you tried to make everything with that. And it was, I was in that position at the beginning, and it was, one of the advantages of youth is not knowing how much you don't know. And so just plunging ahead, and so, well, I can make a cut like this, and then I have to make it over here, and I just tried to make it work, and gradually got closer and closer to what I needed to make. So it was much more crafty, I guess is the word. It's much more hands-on, and there are a lot more failures. Sometimes the saw blade would break. Sometimes I would go offline, and it's, oh crap, now I have to start over with a new piece of wood. And it was much more hands-on, and very much less precise with the handsaw. Now, if I needed to make a circular part or semicircular part, a router makes a big difference, because I can make a pretty accurate circular part. But it's just more hands-on in a shop, whereas on a 3D file or even a 2D file, but I would say forget the 2D files anymore. 3D file, I'm just at the computer, working everything out and making sure everything fits, and seeing and trying to imagine if these ideas are actually going to work, and then having the parts made, trying them out. And in my case, the parts I've had made off my 3D files have all worked out. I haven't had to have them redone. But I kind of came in on the very first wave of this before 3D printers. So I haven't had any 3D printed parts made for me. I've bought 3D printed reflex finder from Rob Brown, his Quinsight, but I haven't made any myself. Although I could, I just haven't felt the need to do that yet.
I think this will be my last follow-up, but follow-up on that. I haven't had the luck that you have with your first 3D printed or like first 3D designed parts working out the moment you cut it. I guess you've probably seen me talk about my board not coming the way it should have and the mistakes I made. So clearly, there's a lot of your decades of telescope making experience that informs how you design and think about things in CAD such that they end up working for very first time, right? So what aspects do you think you draw on the most from your experience when you sit at a computer and design something? Like, what is the most intense bit of thinking? Like, I know balance is a major issue for Dobbs, but what other considerations are you bringing in when you design any particular part based on your experience?
Yeah, well, that's the key word, experience. I've been an observer for longer than I've been a telescope maker, not by much, but a little bit. And I think that combination has just built up to where I have a good feeling for how things are going to work. But also, one of the great things about amateur telescope making is that no one's design is copyrighted. I like to look at telescopes that I know are successful, especially ones I've been able to look through and go, okay, that works really well. I'm going to copy that as close as I can in my telescope. And but this part from this other telescope, this feature is really good too. So I'm going to combine that into my telescope. And in fact, my 28-inch f4 telescope is a combination of Dan Gray's design, the 28-inch telescope, and Tom Ossipowski's 24-inch spike eye telescope. And I basically just kind of combined those and came up with my version. And and knowing these things already worked separately gave me a lot of confidence of that they would work together really well. And fortunately, I was right. As I mentioned earlier, not every one of my ideas works. I've had some absolutely genius ideas that are total failures. And I didn't find out until I'm actually installing it on the telescope. And I go, wait a minute, that's not going to work at all. So it's, yeah, it's a mixed bag. Experience doesn't always mean I come up with the right solution. And I'm sure that's true for pretty much everyone, except for Mel Bartels. Mel really is a genius, and he always gets it right.
Actually, there's one more question on YouTube, which is kind of interesting. How many clear nights do you get on average in a year? And has this number decreased over the years? I'm sure the answer to the last part is yes, because of wildfires. But
well,
go ahead.
I used to count how many clear nights I observed, how many nights I observed, and that's fewer than the number of actual clear nights I get, because life doesn't always line up with clear nights, as we know. So I don't know if they've increased or decreased. I think it's just different every year. I mean, the last time I counted the number of nights I went out and actually observed was probably, I don't know, 15 years ago. And it's like, like 35, 36 nights a year. And I wouldn't be surprised if that number is pretty much the same now. But but that was when I was working. Now that I'm retired, I have the opportunity to go observe more often, even though I don't get every clear night. Many times the grandkids come first. And, but yeah, I think that my total number is probably pretty much the same. Yeah, like I mentioned right at the beginning, we have a 9-month rainy season, which we're in the heart of now. And well, actually, we're in the final third. It goes from mid-October through the end of May, early June usually. And I had 4 good nights this January. On Monday, I'm heading out to a dark sky site for a couple of nights. Chickahominy in Central Oregon. It doesn't always work out in March, but usually in April I'll be good. I'll see you at Jimmy's place in May, and then the summer star parties start in early July. We'll see you at Golden State. In fact, I'm going to try to hit Golden State and then immediately following go to Oregon Star Party. That'll be interesting. And then the wildfire smoke season will pretty much shut down the rest of the summer, probably. It's a pretty good guess anymore. And then, if there's a clear night or two in there when the smoke blows away, then I'll take advantage of that. But the actual weather patterns here have been slowly changing to the point where the mountains are getting less snow than they used to, which is why we're getting more wildfires in the summer. But that has been increasing the cloudiness in the middle part, in the early part of the year. But sometimes summer starts in early May. So yeah, climate's changing. There's no doubt about it. Yeah.
I think that's all the questions there are. I think let me thank Howard, and then we can cut the live stream. I'll still watch if there are questions so we can pick them up in case they show up. Yeah, thank you, Howard. This is the second time you've done this for a BAS. I'm really thankful, and I'm sure all my fellow BAS members are equally thankful for you to take out time out of your schedule, and especially wake up earlier than usual at 9 in the morning, which is absurd in astronomer hours.
Yeah, yeah,
Come
that's
and
me.
talk to
I'm a night
us.
owl.
Yeah, and I intentionally set this up after daylight savings, so kicks in so that at least mentally
Thank
we,
you.
we think of it as 9 a.m. even though it's effectively the same time as 8 a.m. Right. So thank you very much, and I think you will be delighted to know that your talk was heavily watched. It's one of our top watched videos on our YouTube channel, and
Oh, wow.
I've heard it around to many people who ask me about sketching, including a 16-year-old in Idaho who's a very enthusiastic visual observer. You might meet him at you might meet them at OSP. And yeah, so that's one thing. And I think we also had an audience of about 20 or 25 people and a lot of questions. So clearly, there's a lot of interest in learning what you have to say. And thank you for coming and doing that for us.
Oh, my pleasure. My pleasure. Yeah, just as an aside, this past Wednesday, just a couple of days ago, I went to a local high school and gave a talk about sketching, and it was great because it was such a small group. We didn't even use the projector for my laptop. We just kind of all sat around my laptop, and the back and forth and the interest of these young students was really encouraging. That not only are there some high school kids who are interested in astronomy, but are interested in sketching. It's like, wow, okay. I came away from that feeling really, really positive. That this just isn't an old person's hobby, like some people seem to think and bemoan about all the time. Um, so yeah, I'm always up to talk about sketching or telescopes or observing. Yeah, so I'm very appreciative of your invitation and coming back, um, and then hearing that sketching presentation I gave in October went over so well. So thank you all very much.
Likewise, thank you very much, Howard. With that, I will end the live stream.